dar inicio a este tercer encuentro de las charlas que está organizando la Comisión de Petrología Ígnea y Metamórfica de la Asociación Geológica Argentina. Les damos la bienvenida a todos y le damos un agradecimiento muy especial al doctor Willner por haber aceptado la invitación de dar esta charla para todos nosotros. Hacer una presentación del doctor.
Bueno, muchas gracias, Flor, y bienvenidos a todos desde Alemania. Ahora ya es la tarde aquí y había un lindo día de verano. Disculpen, por favor, los problemas técnicos y disculpen además que voy a seguir a hablar en inglés y simplemente porque ya por mucho tiempo sin contacto con el mundo sudamericano me siento más fluido en inglés. Ok, voy a hablar sobre la colisión de Chilenia y un I will talk about the late Devonian collision of Chilenia and an interrelated process of the early Carboniferous initiation of subduction in Chile. So these processes give further information about the existence of Chilenia, I think. So I choose as sort of introductory figures two photos from the Cordillera Principal, con vista with view seen from Chile and from Argentina on the right side. This massive block of mountains hided enormously lot of important information on the Andean basement. Moreover, it's a sort of wall, a wall not only in the physical sense, but also in the mental sense. So workers on either side quite often do not look on the other side. So I had the great opportunity to work on both sides of the end of this principal Cordillera, and so I feel justified to make a sort of synthesis of this, my former work. So in the South American continent, in the area of Argentina and Chile, was growing during the Paleozoic times in a very classical view. It started in the east with a big accretionary prism in the late Proterozoic Cambrian times. This prism was incorporated partly also in a magmatic arc. This is all the Pampine orogeny that likely ended with a collision of a small microcontinent. So in the whole was later in the Ordovician incorporated in the enormously wide Fermatinian magmatic arc. And during the activity of the Fermatinian arc, the continent, a microcontinent called Chilenia, collided, and in the western Pampine Sierras, we have a sort of collisional wedge, and then afterwards, sorry. We have a sort of collisional wedge, and then the leading margin of South America after this collision jumped on the western side of the Precordillera. Here another collisional belt developed, and then after late Devonian times, another jump of the leading margin occurred to the present Pacific margin. So the continent grew by accretion and also by collision of microcontinents. So I will talk about these latter two geodynamic environments, the collisional belt and the late Paleozoic active margin. And in between, all this happened around a supposed microcontinent of Chilenia. I will not talk about geochemical work, intensive geochemical work done on magmas that later intruded this area, where studies of magma contamination, of xenocrust, of xenolith showed that the whole is underlain actually by Mesoproterozoic basement. This is nothing special because the whole margin, Andine margin, or the whole Andes more or less are underlain by Mesoproterozoic basement. And this is also not unusual because we know at least since the work of Ian Dial in the 1990s that South America was once attached to Laurentia across the Granvillian origin in the macrocontinent of Rodinia. And when this broke apart, a lot of small microcontinents were released. Okay, let's go first to the supposed collisional belt on the western edge of the present Precordillera. So it was Victor Ramos in the 1990s who observed a chain of ophiolitic rocks along that margin, and he proposed collision between what he called Chilenia microcontinent, and he introduced first a Chilenia microcontinent. So I will not talk about the geochemical evidence or the geochemical content of these ophiolitic rocks. There is a vast amount of work done by Graciela Vujovic, by Flor Boedo, and others, finally showing that there are a lot of different sorts of mob basalt present from different ages, and they could show that even a time sequence of evolution of these former basaltic rocks from a rifted margin to a full oceanic stage. So this all is reconstruction of an evolution prior to collision. So still, people are still questioning. They're questioning still still the existence of collisional wedge, and they are still questioning an existence of Chilenia. So I even was also earlier on, when I only worked in Chile, a bit skeptical and thought, ophiolitic rocks also may occur in accretionary prism, and why is it not the start of an accretion that propagated to the present margin? So I went to the structural lowermost part of this belt that was called mafic ultramafic belt by Victor Ramos, and here we have the rocks in a metamorphic medium grade. We have medium grade metamorphic rocks, and whereas the other remnants of this wedge are in a relatively low metamorphic grade. Okay, what happens here? We studied the major rock types: garnet amphibolite, garnet mica schist. We applied two different methods to get PT conditions. We started with multivariant equilibria method, combining the compositions of mineral cores and rims. And later on, we also applied pseudo-section approach. With that one, it's much easier to get PT conditions, for example, of garnet cores, garnet rims, by simply intersecting compositional isoplates. So what we ended in was a clockwise PT path with PT conditions of about 13-14 kbar, around 500 degrees Celsius, and then a decompression path with slight heating. And later on, cooling at lower during exhumation to lower pressures. The same PT path could be the same maximum condition could be observed in both different types of rocks we see there. And we dated peak metamorphism by a method that involves garnet, lutetium hafnium. We produce lutetium hafnium isochrons, mineral isochrons, and got 4 isochrons, 3 4-point isochrons with an age around 390 million years. So quite hard data. White mica argon ages are at around 350. Maybe these are cooling ages. Maybe and I would see it now like this: a retrograde deformation, and later a fission track zircon ages dating the cooling under 280 degrees. So from this we can derive exhumation rate that exceeds 1 millimeter per year. That is much higher than average erosion rates, and it's quite typical found in collisional wedges. The whole ends, by the way, in that area with post-collisional granitoids that are lower Carboniferous. Okay. So what does this mean? What does this high pressure condition of 12 to 14 kbar and temperatures around 500 degrees mean? Considering two alternatives, collisional wedge or accretional prism. These are actually the main geodynamic environments where high pressure rocks occur. So So these high pressure conditions overprinted in the Guaguaras complex overprinted neritic sediments with a maximum depositional age of around 560 million years. It's from information from your dating detrital zircons. And they also contain Venian, Cambrian Acritake. So same conditions were derived, same high pressure conditions were derived from garnet amphibolite, and these have protoliths with chemical morph signatures and samarium neodymium Hurok isochron age of 650 million years. So there is a considerable time gap between deposition at a Neoproterozoic passive margin and late Devonian high pressure metamorphism. The peak of metamorphism exceeds 10 kbar, and we also observed an early decompression heating path, and all these point to an evolution in a collisional wedge. Just by contrast, in an accretionary prism, we get turbiditic trench sediments that are accreted and overprinted, and they were just deposited slightly before the metamorphic imprint. Peak pressures in accretionary prisms hardly exceed 10 kbar. Recent and sub-recent accretionary prisms have a maximum depth of 40 kilometers. And as we will see later, PT paths in accretionary prism are characterized by decompression cooling paths. So, and what does the age of the high pressure metamorphic peak in the Guaguaras collision complex mean? So we have quite hard ages. And these ages, around 390 million years, are the oldest so far known ages of high-pressure metamorphism in this particular collisional wedge. They indicate when these rocks reached maximal boil. So, but initiation of collision between Chilenia and Cuyania must have been slightly before, so I assume a period around 405 million years, appears quite realistic due to some potassium-argon ages in the precordillera sediments, and this is relatively new, abundant argon-argon white mica ages in the Sierra Pie de Palo, which at that time was in the foreland area during the collision. And here these ages indicate late retrograde deformation. So you see here a collection of all published and still unpublished data in the Sierra Pie de Palo, and here we see a quite pronounced 405 million year peak. Okay, all this belongs to the chanic orogenic phase, and we can say the chanic orogenic phase is evidence of a microcontinent collision. Florencia Boedo also studied PT conditions in the Peñasco Formation, Ordovician Formation, that certainly belonged to the overriding Cuyania plate. Got PT conditions that are on the same low metamorphic gradient of 10 degrees Celsius per kilometer as our Guaguaras rocks. In another area, in the foreland, in the Djerba Loka formation, other people got found low P and T conditions. So these are not from a part of the actual collisional wedge. And I also draw briefly your attention on condition and dating by Martinez in some area near San Carlos de Bariloche, with much higher pressures and the same age of 390 million years. I will come to this much later at the end of the talk. Okay, a brief scenario. What collided are two margins, two rifted margins, and collision must have been flat. Always asked or pointed out, well, you have a collision and there is no magmatic arc. So, for some people it seems to be a natural law, but every Andean geologist knows that there are amagmatic segments where subduction is flat. So if you have a flat amagmatic subduction, you can also have a flat subduction, a flat collision. A very good example for this are the Alps. In the Alps, the upper plate, the Adriatic plate, does not contain any magmatic arc. So, collision probably even both continents were at around 400 million years, quite near. But at, say, 380 million years, there was certainly a full collision. And in the collisional wedge, we get mixture of both the upper and lower plate. So, so if we have a continent collision, and we say it's a collision between Chilenia and Guyana, there must be, on the other side of this microcontinent, there must be a passive margin. And some later time, this passive margin must be converted to an active margin. And this is what we actually see in the Pacific margin of Chile. All this starts around 340 million years, and on Chilean territory there is nothing, absolutely nothing pre-Carboniferous to be seen actually in central Chile. So by this we leave the collisional complex in the Goa Grass in the Frontal Cordillera, and we move on to the Chilean side, the accretional prism in Chile on the in the coastal Cordillera of Chile. And in this marvelous site, we also have a very peculiar rock. And this rock occurs only at 3 different points in the whole central Chile. So from the area about Los Vilos down to Puerto Montt. So these special rocks are relict rocks from the subduction channel within these late Paleozoic accretionary prism. And these rocks show the highest PT conditions compared to the surrounding rocks in the accretionary prism, the highest ages of metamorphism, and an anti-clockwise PT path. And these conditions all are typical for the initiation of metamorphism. So I will have a closer look to an occurrence in near Los Pabilos, near Valdivia, already in the 1980s. This rock was found, described, and incidentally studied by Terence Cato. Here we have an overprint of 2 completely different metamorphic assemblages. An assemblage with garnet, hornblende, rutile epidote is overprinted by a later one with chlorite, titanite, phengite, glaucophane. So with multi-equilibria approach, we got PT conditions for the first stage at around 15 K bar and temperatures up to 700 degrees. And then for the second assemblage, the blue schist assemblage, we get similar peak PT conditions, and then we can also trace cooling decompression path. So it's a sort of initiation of, or it's a sort of part of an anti-clockwise PT path. So we dated the first stage with Lutetium hafnium garnet or mineral isochron at 340 million years. Unfortunately, this age is only published in an extended abstract, and I did not mention it to manage to publish it in the meantime. And in earlier rubidium strontium mineral isochron involving white mica, so dating the blue schist assemblage, yielded an age of 305 million years. Later and early PT pseudosection approach, here only seen in a simplified version, was showing the PT fields of respective minerals. We found we got a prograde PT path from composition of amphiboles included in garnet. And we could also reconstruct the early cooling, isobaric cooling path. So in total, we have an anti-clockwise PT path. So these two ages, the garnet hornblende assemblage and the fingered glaucophane assemblage, and also we have from the surrounding garnet mica schist ages of 305 and 340 million years are much higher than in the metamorphic ages in the surrounding accretionary prism, which are at around 250 to 260 million years. Okay. What does this mean? How does what scenario is standing behind these special rock types? How can we explain these special rock types? And instead of a simple diagram, I will present you with a small animation of a modeling by my colleague Taras Geria from 2003. He produced a numerical modeling involving collision of oceanic or subduction of oceanic crust with low oceanic crust, involving some sediments, realistic thermal grid. Yes, the hydration of the mantle due to fluid infiltration could also have been modeled. The subduction was initiated by introducing a initial weak zone, and we also got realistic subduction rates were ingressed into this modeling. So we start modeling, and we can observe here a point that is subducted first during initiation of subduction. During subduction, we see here in the PT path that this rock is continuously heated. It's heated because the mantle wedge is still hot. It arrives at its finally destination at pressures around 20 kbar. And then an isobaric cooling starts because more cold material is subducted beneath that rock. So isobaric cooling continues as more cold material is thrusted underneath. And then we can now observe the subduction of a point that is later subducted. It also gets heated and meets the early subducted rock, but from that on, rocks get exhumed along a path that is shows cooling with decompression. And after about 26 million years, these rocks meet depths that are according to an accretionary prism. Okay. Coming back to the distribution of these subduction channel rocks, the peak ages are always much older than the ages in the surrounding rocks. Here in all three occurrences. The oldest ages are in Los Babilos with 340 million years. In near Pichilemu, the initiation must have been before 320. In the north, before 307 million years. These ages derived from white mica argon-argon dating. And I'm sure so far nobody had the idea to date the garnet either by lutetium hafnium or neodymium samarium, that actually there are still older ages in these rocks present. Anyway, we have an idea when the subduction started due to these rocks that only originate at the beginning of subduction. Similar situation seen now in many places in the Caribbean, in the Franciscan of North America, and I recently got to know many places in the Himalayas where the similar story happened. So, how does the story continue? We see in this map that there are two distinct belts, so-called Western and so-called Eastern belt, and these are characterized by very different modes of accretion. In the northern segment, these have somewhat different ages, but it's almost the same, the Arayan and formation in Chapa metamorphic complex. So in the 1990s, Nina Korkowski in Potsdam made quite a lot of analog modeling with sand, in a sort of sandbox analog modeling, studying the accretion process, and it was Johannes Glotny who was the first to compare these results with accretion complex in the Valdivia area. So what happens here? We see that the first frontal accretion produces folds and thrusts, and so the accretion prism is horizontally propagating towards the trench. It's a thickening flow field. The final compression is more or less horizontal. And with time, in the sandbox modeling, introducing increasing internal friction, material is subducted underneath and basally accreted. Basal accretion is in a more or less subvertical compression, sort of flattening or a thinning flow field. So in Chile, we find both an early frontal accretion the eastern series, and then followed by the basal accretion. So how does it look like? In the eastern series, we find first folding of bedding planes of these greywackies that were deposited in the trench with axial plane foliation. And even here in this section, we see a second deformation that is already a sort of indicating a sort of flattening. By contrast, in the western series, we observe the basal accretion mode that is characterized by flat-lying transposition foliation, internal tied to subhorizontal isocline subhorizontal folding. Even there are quartz veins that originated during prograde metamorphism, even in the diagenetic stage, are isoclinally folded. So this is a strong transposition foliation, and actually more or less a coaxial deformation. There are only some very local shear bends can be observed. So when did this change of frontal to basal accretion occur? For dating, we can observe ages of maximum sedimentation. These ages derive from uranium-lead dating of zircon. In all maximum sedimentation ages in the frontally and basally accreted rocks are Carboniferous. In the frontally accreted, they're slightly older than in the basally accreted units. The youngest one we observe in the basally accreted Troappas complex with 311 million years. So if we observe the age of peak of metamorphism, which is equivalent to the accretion process, we see the oldest age of 308 million years in the Western series. The eastern series in the north are not overprinted by later high temperature metamorphism, but the eastern series, these are not overprinted, but the eastern series in the southern segments are overprinted at 300 million years, as we will see in the following, and in the frontally accreted and non-overprinted areas in the northern section, we must derive an age of more than 310 million years for the first frontal accretion. This age comes from zircon fission track dating. Argon dating in that area is strongly overprinted by Mesozoic processes. Okay, so from this age, and this age, we can derive that 308 million years is more or less the point where these accretion modes changed. There's only one section in entire central Chile near Constitucion, around a section along the Rio Marula River, where we can actually in the field observe the transition from between both accretion modes. Everywhere else, this sequence is somehow interrupted. So here we can have a full profile. And Peter Richter made an intensive study of final strain parameters and found that strain is strongly increasing and continuously increasing from the eastern series to the west into the western series, say from these dark shading to the more whitish colors. This continuous evolution is interrupted elsewhere, like here in this along this post-Carboniferous fault, and in also there are many other areas where this transition is simply covered by younger rocks. We have also an idea why this accretion mode changed. Here we see two PT pseudosections that are based on Greybecke compositions, here of an average metamorphosed Greybecke, here of a Greybecke from the Western series in Chile. Shown are isoplus of water in solids in weight percentage. So these isoplus show how the dehydration is distributed in the PT field. And we see that it's not randomly distributed, but there is, at low temperatures, there is a zone of maximum dehydration. So this is roughly the same in both rocks. We could also show it's the same in hydrated metabasites. And if we ingress the prograde PT path or supposed prograde PT path of the frontally accreted rocks and the basally accreted rocks, we see that the frontally accreted rocks were submerged under a higher metamorphic gradient. That means these rocks reached their maximal depths when they crossed the dehydration zone. So water is released. This release of water leads to softening of the rocks and aids accretion. Later, the isotherm cooled, and the basally accreted rocks could get into greater depths and reached the zone of dehydration at a deeper depths and a higher temperature. So it appears that in nature, the different accretion modes depends on when the metamorphic gradient. In subduction channel rocks, for example, the rocks can be submerged under a much lower metamorphic gradient to much greater depths. So, and the whole actually process that is behind is a continuous cooling of the convergent margin that is observed in many other convergent margins worldwide, a common process. So back to the metamorphism. The high pressure overprint we find in essentially in the Western series. In the Eastern series, in most of central Chile, has a high temperature, low pressure overprint. This we see here in this figure, for example, in iso grades of storal andalusite iso-grade passes to a sillimanite iso-grade, and finally to a cordierite garnet K-feldspar iso-grade. So there is increasing metamorphism at low pressure towards the intruding late Paleozoic batholiths. So these observations were made quite early, In early stage, the high pressure metamorphism was recognized by some few findings of blue schist, and people already thought that this would be a typical example for a paired metamorphic belt. But to fit this definition, we need dating. And if we have a look first at the conditions of these rocks and what rocks are at all in the Western series, we have seen there is a huge amount of metagravices. Blue schist lenses are included. These blue schist lenses are quite frequently overprinted by green schist facies metamorphism. However, 90% of all metabasites in the Western series are green schist, here with relic pillow structures. And there are also some more rare rocks like black schist with spessartine quartzites, also known as corticules. So these are enrichments of manganese and iron, likely from hydrothermal activity or simply precipitation from at the ocean floor. The high pressure indicator in the blue schist, of course, is glaucophane. Glaucophane is missing in the green schist. The peak high pressure mineral in the green schist is a calcium sodium amphibole called windschite. So windschite is typical for these high pressure grain schists. These high pressure grain schists, as I will show, have never been blue schist. There is simply both were accreted in the accretional prism, but there is a definite pressure temperature difference between them. Another high pressure indicator is phengite in both metabasites and also in the metagravices. Phengite is a white mica with its eye contents exceeding 3.2 per formula unit. In the accretional prism here, they even reach 3.5 SI per formula unit. So this already indicates quite elevated pressures. Again, originally with a multivariant equilibrium approach involving assemblages with white mica, amphibole chloride, epidote, and quartz. We could derive points along a PT path. A typical or maximum conditions of around 10 to 12 kbar in the blue schist and about 8 to 10 kbar in the green schist occurred, and in both there are we can observe cooling decompression paths. So this is quite typical for accretional prisms, but still both different metabasites come from a different depths. This we could also confirm already with a quite early PT pseudo section here, based on green schist composition and on a blue schist composition, that there is a transition zone between sodium amphiboles and calcium amphiboles, and this transition zone is at the same PT conditions in both cases. So the sodium amphibole actually, the blue schist must have occurred must have been overprinted at higher pressures than the green schists. Later on, we could, with later PT pseudosection, we could show that actually in this transitional field, we can find compositions, calcium, sodium, amphibole compositions. So what happened to the eastern series? How were they metamorphosed? There are two metamorphic stages. One stage, an early stage during frontal accretion. This is difficult to get because mostly, as I said, in central Chile, the eastern series is overprinted by this high temperature metamorphism. In the northern section near Los Vilos, in the Arrayant Formation, we do not see this high temperature metamorphism, and we got at least an idea about the pressures. They are between 4 and 5 K bar, and temperatures likely between 250 and 300 degrees Celsius. In Patagonia, we have much better evidence, or much better PT data for these frontally accreted rocks by later PT pseudosections. Also, in the northern section, there is a retro-wedge basin, the Loken Formation, with much lower pressure and temperature conditions. In the high temperature, low pressure overprint, we get conditions of only 3 K bar and temperatures between 400 and 700 degrees Celsius. Okay, if this is a true metamorphic belt, we must know the ages, and paired metamorphic belt must show the same ages of metamorphism. So we applied argon-argon dating on white mica, mainly in metapilitic rocks, also in metabasic rocks, and they are all around 300 million years, 290 to 300, but also here in the eastern series that are overprinted by this high temperature, low pressure metamorphism. And also uranium lead age of the coastal batholiths in this area shows the same age. So what we see is frontal accretion at the same time as the metamorphic overprint in the relic eastern part of the accretionary prism that is intruded by the coastal batholiths. So a true paired metamorphic belt. We also got zircon fission track ages and apartheid fission track ages, and from this we could derive exhumation rates. Exhumation rates first started to be around 0.2 to 0.5 millimeters per year. This is actually corresponding to average erosion rates. So much lower than we observed formerly in the collisional wedge. So what happens is that during basal accretion, elevation forms at the surface, and this is eroded. So basal accretion and erosion at the surface is sort of balanced. With time, we see here with the ages of cooling under 280 degrees are at around 230 million years, around 100 million years, the cooling under 100 degrees Celsius. We see here the derived exhumation rates are steadily declining. The same happens in the eastern series that are only heated in shallow depths of 3 bar, and their exhumation rates are similarly very low. Okay, we put all this together into a full-scale cross-section of this central Chilean coastal accretion system near Constitución. At the height where this accretional prism is least deformed. In many areas, subduction erosion occurs. In other areas, later or post-Carboniferous deformation. So we see PT path, the path of the green schist being the green schist rocks, the western series being steadily exhumed. Here the PT paths for the blue schists, and here the path for the subduction channel rocks that were subducted first. It's a bit over exaggerated, and dehydration here under the mantle wedge does not occur simply from these subducted sediments, but also the oceanic crust certainly is dehydrated, and this inner is here in this modeling inner depth that is appropriate for this dehydration. Okay. Meanwhile, the eastern series are only found as relics, as frontally accreted early relics, and they are intruded by the coastal batholiths. So all this together in a sort of time sequence. We start here with the earliest, deepest subduction in the subduction channel under a still hot mantle. So then a cooling path occurs. Then frontal accretion of Greibeckis occurs, horizontal flow and horizontal compression, and very rapid propagation of the leading margin towards the trench. So the margin is growing considerably by this process. And then around 310 to 300 million years, the accretion mode changed to basal accretion. So the western series are accreted at much greater depths. And here in the rear of the frontally accreted eastern series, intrusion occurs and metamorphic, low temperature metamorphic overprint. So in the time 300 to 220 million years, we get continuous basal accretion balanced by erosion. Material is recycled into the trench. With time, the magmatic arc activity is waning, and at around 220 million years, the story ends. Nothing is accreted anymore, likely due to climate change. Cyclic mass flow comes to an end, and there is a major change in the margin configuration from a compressive convergent margin to an extension conversion margin. So the same sequence we have in further north, in the so-called shallow slab segment, where the magmatic arc does not intrude here near the coast, or into the earliest frontally accreted rocks, but much further inland in a retrograde basin that is found there, and the slab is much flatter. So again, all this happens between roughly 320 million years and ends at about 260 million years. Okay, ending the story, I will end this with a sort of provocating view. I often was asked in the past, what is the extent and the origin of Chilenia? Where does it come from? Where is its ending? We have seen here in the that the late Paleozoic margin evolves more or less in the same way from about Puerto Montt to Chañaral in the north. So with different segments, to shallow slab segments and the central steeper slab segment, but more or less we have the same evolution starting in the lower Carboniferous. South of Puerto Montt, the story is quite different. The margin is wider and much younger, Mesozoic. North of Antofagasta, we have a completely different underlying terrain, the Arequipa Antofalla terrain. That is actually Mesoproterozoic terrain, Greenvillian terrain that is extending into central Peru, and its characteristic and the margin of the Ordovician Farmatinian margin here jumps to the coast up to central Peru, and this terrain was evidently collided much earlier than the Ordovician times. So there is a firm boundary. The extent of Cuyania is a bit difficult. We can, in boreholes, pre-Cordillera rocks are found at several places, in the San Rafael block, for example. Also from the collisional wedge, there may be a continuation, so metamorphic rocks are found further south, although the PT conditions are yet unknown. So at least roughly, this is the western limit of the Farmatinian arc. And so Cuyania may exceed in this area. However, if I showed that the collisional wedge between Chilenia and Cuyania is at least 300 kilometers long. And the PT conditions, the high pressure, the Devonian high pressure conditions in the Guaguaras complex have their equivalent in the south, near Bariloche. So it's likely that this collisional wedge extends. South of the Guaguaras complex, we find evidence of a Devonian magmatic arc, also in the south, north of Bariloche in two places. So it seems that there is an extensive Devonian magmatic arc undercover. So, and also the Devonian margin was evidently segmented into a amagmatic and a magmatic segment. Okay. If we take this here as the eastern boundary of Chilenia, I would end up with 2,000 kilometers of extent of Chilenia, underlying almost the entire central Chile, and with a width of about 200-300 kilometers. So at the first glance, it might seem improbable, but I ingressed the recent situation at the Pacific margin in California at the same scale, exactly the same scale. Here, presently, the East Pacific rise is cutting into the continent in the Bay of California, producing oceanic crust. The whole ends here at this famous San Andreas Fault. In some million years, this will propagate and finally separate a sort of microcontinent that has more or less this extent of my proposed Chilenia. So 2,000 kilometers and sort of 200 to 300 kilometers width. So Chilenia might have been cut out originally out of Laurentia. It also might have been cut out of Cuyania during Cuyania's approach to Gondwana, or it might have been stayed in this sort of peninsular stage. So for some time, some part of Chilenia might have been simply peninsula to Cuyania with a relatively small oceanic crust in between. So this is just to keep you thinking, maybe fighting and discussing around it. And with this, I would like to thank you for your attention. Okay. ¿Me ven? La mitad, por lo menos. Ok. Hola, Pancho.
Hola, Arne. ¿Cómo estás? Qué gusto. Perdón, voy a tomar la palabra entonces. Arne. Qué gusto de verte bien después de todos estos años parcialmente escondidos que hemos tenido. Y quiero felicitarte por tu charla. Es una charla muy bonita, muy bien expresada, con mucha información, como siempre han sido tus papers. Así que es muy iluminador, digamos, escucharla de esta manera integral, como ha hecho hoy día. Así que, y con el modelo de California, que es algo que realmente es algo necesario de trabajar. Así
claro,
que,
claro, es una idea.
Es muy buena idea, es muy interesante como idea, así que yo creo que como todas estas ideas grandes no es fácil de producir todos los argumentos, pero yo creo que impulsa mucha investigación y eso es lo importante.
There are many points that needs more investigation.
Así es nuestra ciencia. Algo que yo no sabía o no había reparado son esas isócronas lutecios hafnios que has hecho y que dijiste que se estaban presentadas solo en un paper de un congreso.
Sí, en la de Santiago de 2009.
Ah, fue en Santiago, mira, yo no me había dado cuenta.
Tú, estando en tantos otros proyectos, así que no todavía no podía publicarlo, ¿no? Y siempre, ya.
Interesante como dato, vamos a tratar de rescatarlo también yo para verlo mejor.
Pero también dije que también en Punta Serena, en los Vilos Aéreos, necesitamos datar también el granate. Seguramente obtendremos edades más tempranos para el inicio de subducción.
Sí. Hay otra localidad donde se encontraron estas amfibolitas de granate con trayectoria antihoraria, que es en Los Choros.
Sí, ese leído, sí. Pero con condiciones y edades muy similares a...
sí, claro, es muy parecido, pero es otro
lugar.
lugar, digamos, donde aparece este tipo
Sí.
de... Así que nada más puedo agradecerte, felicitarte y estoy muy contento de verte.
Bueno, gracias. Me gustó de verte.
Eso, muchas gracias a quien...
Bueno, le damos la palabra a la doctora Renata Tomesoli, que quiere hacer unas consultas.
Gracias. Bueno, otras preguntas.
Hola, buenas tardes. Gracias por la exposición. Hola, ¿me escuchan bien?
Sí. Sí. Perfecto, sí. ¿Me ves por lo menos mi boca aquí?
Gracias por la exposición. Quería consultarle si alguna vez pensó en la posibilidad de que Chilenia fuera parte de Patagonia, que fuera parte del mismo continente, o sea, la prolongación de Chilenia. Lo que se ve en todo el margen sudoccidental de Gondwana son exactamente las mismas edades que se ven en el margen de Chilenia, una deformación que comienza en el Devónico y continúa superior.
No sé, capaz refieres a ese datos de Juan Cruz Martínez, que encontró ese rocas de alta presión con la misma edad de 390 como en el complejo Guagarás. Bueno, es definición, si eso ya es Patagonia. Eso he mostrado en el último imagen, es más o menos a la altura de Puerto Montt. Es el punto muy parecido a Guagarás, pero el punto más al sur austral que conocemos. Sí, muy probable que el complejo de colisión de Cuyania Chilenia extendió a este punto. Ese es el punto más austral. En el sur de Puerto Montt, por supuesto, también existen prismas de acreción, pero las edades son mucho más jóvenes. Lo que ocurre al este de eso, no sé.
Entonces, me voy a...
Es para mí un punto más austral de evidencia, de posible evidencia de ese complejo de colisión. Y además en esa zona también hay evidencias de un arco magmático devónico que también ocurre un poquito al sur del complejo de Guagarás.
Bien,
así que el margen devónico puede extender desde la cordillera frontal hasta la altura de Bariloche. Es posible. Hay dos evidencias, por lo menos.
Voy a aprovechar la audiencia y a los colegas, entonces, para que me ayuden a pensar la posibilidad de que Chilenia y Patagonia hayan sido parte del mismo continente, ¿sí? Para que podamos pensarlos entre todos.
Bueno, hay mucha cubierta. Puedes también pensar que antes de emplazamiento de Chilenia habían más microcontinentes. Por ejemplo, si van al norte de los Apalaches, en Norteamérica, ahora la gente han encontrado un montón de microcontinentes. También yo estuve envolvido en detalle en de estudiar esos complejos de colisión allá. So, la cosa queda más complejo que la gente pensaba antes. So, hay más microcontinentes, más complejos de colisión y desgraciadamente en Sudamérica, entre la precordillera en Argentina y Patagonia, hay muy poca información, mucha cubierta. Hay aún más cubierta debajo de la cordillera principal aún. Así que tenemos que contar con pocas informaciones locales.
Bien.
¿Puedo hacer un comentario?
Simple. Hay gente que piensa que Patagonia, otra gente que piensa que Patagonia es un microcontinente mismo, que piensan que en el macizo norte de Patagonia hay una estructura este-oeste con rocas calcalcalinas. La gente piensa que eso es también una zona de colisión por la ocurrencia simplemente de magmas calcalinas. Pero por ejemplo, encontramos allá un arco famatiniano que se extiende hacia el sur. También hay evidencias que rocas pampeanas extienden hacia el sur. La continuación de esa estructura este-oeste también estudiado solamente en puntos. Es más o menos una consideración hacia si se continúa hacia el margen chileno, se ve ahí la falla de Purén o falla de, ¿cómo es ahora?
La Nalhue.
La Nalhue. Estado muy intensivamente Pancho RV. Y ese es una simple falla. Me parece que ese era originalmente una falla de ¿cómo es? De transforma que entra desde la corteza oceánica hacia el continente. Más tarde se convierte a una falla de cizallamiento. Pienso el argumento mayor para mí es el mapeo que Pancho hizo en 1977. Ahí se ve que el arco magmático no es simplemente desplazado, pero que el arco está, el metamorfismo de ese arco está imprimiendo a esa falla. Así esa falla de la Nalhue o línea de Purén es separado simplemente dos segmentos del margen con diferente geometría del slab. Sí, un shallow slab and a steeper slab. Bueno, si es así, si es una falla de transforma, es cortando muy hacia el continente. Pienso que esos rocas alcalinas simplemente intruyeron porque es una porque puede ser en una falla de transforma. Es una idea. Para mí todavía la evidencia es no claro que esa es una zona de colisión entre dos continentes. Todavía estoy saulos para eso. Nunca fui a esa zona y parece que no tengo la oportunidad de estudiar ahí, pero es una simple idea. Es una reservación. Antes también tenía un poquito la misma reservación en contra de esa zona al oeste de la precordillera argentina. Antes que se cambió completamente cuando me fui a estudiar ahí. Es todo que puedo decir. Es nada más que idea.
Yo quería comentar, Renata, que la hipótesis que ustedes presentaron en un congreso en Chile también fue, ¿no? De que Chilenia y Patagonia podrían estar unidos. Es una opción interesante. Que difícil de demostrar completamente, pero también difícil de descartar. Entonces, es muy estimulante para realizar estudios más de detalle en el asunto. Tenemos esta zona inmensa con poca información finalmente. Entonces, nosotros ahora último, y quiero concluir con eso, hemos visto que hacia el sur de Puerto Montt, por ejemplo, y un poco hacia el norte de Puerto Montt, hay muchas rocas magmáticas, plutónicas, devónicas, en la costa de Chile, que no conocíamos hace 10 años.
Ese mencionado, ¿no?
Entonces estamos ahí también pensando cómo interpretarlo. Y hemos inicialmente pensado que puede ser un elemento diferente de Chilenia, que lo hemos llamado por el momento Chaitenia. Porque cerca de Chaitenia están esos...
Pero es más al sur. Más al sur de Puerto Montt.
Sí, no es tanto más al sur que Puerto Montt. Es más al sur, claro. Entonces, entre medio no sabemos. Y Chaitenia, entonces, es otro elemento que podría reemplazar a Chilenia hacia el sur. Porque es un elemento que no existe.
O ahí justo el terreno o el pedacito que nos falta, la pieza que nos falta para completar el rompecabezas entre Chilenia, Chaitenia y Patagonia.
Claro.
Sí, la cosa, ese es el proceso, ¿no? de investigación. Primero, la gente está introduciendo terrenos. El terreno es nada más que una cierta zona con una evolución parecida que es diferente que en otra zona. Con más información, con encuentro, por ejemplo, de rocas ofilíticas, de condiciones de un verdadero cuna de colisión, con más dataciones. Algunos de esos terrenos convierten a ser microcontinentes. Pienso por lo menos en la zona que he mostrado en la zona de la precordillera hacia el oeste, tenemos evidencia de existencia de dos microcontinentes. Esto bastante seguro, Cuyania y Chilenia. La extensión de esos microcontinentes es más o menos interpretación de los datos que existen. Eso es que quería mostrar al último imagen que he mostrado. Bueno, así estamos en todo el mundo, especialmente en los Appalachians. Hay muchos terrenos encontrados que convirtieron ahora al estado de microcontinentes, microplacas. Así Avalonia, Ganderia, Dashwoods y otros. Es un proceso de obtener más y más datos. Así, creo que por la gente que ahora siguen, queda muchísimo, muchísimo que hacer. No estamos.
Arne, acá tenemos una pregunta en el chat. Paulo Quesada pregunta si cuando la geometría de la zona de subducción es de alto ángulo, tipo Mariana, si existe el desarrollo de un prisma de acreción y qué variaciones podrían existir comparado con un sistema de flat slab.
Era un poquito muy rápido esa pregunta. ¿Puedes cortar un poquito? Florencia, tú estás preguntando, ¿no?
Sí.
No te veo.
Haciendo una pregunta en el chat.
Ahora. Bueno, mejor si te veo entender mejor.
Preguntan si cuando la geometría de la zona de subducción es de alto ángulo,
sí,
existe el desarrollo de un prisma de acreción.
La existencia de un prisma de acreción depende del clima. Es porque un verdadero prisma de acreción necesita muchos sedimentos. Al momento hay un verdadero prisma de acreción desarrollando más al sur de Patagonia, en Patagonia chilena. Ahí tenemos un clima muy húmedo, frío, y en zonas más altas existe una zona nival. Así muchos sedimentos son producidos, muchos sedimentos son depositados en el trench, en la fosa. Y así existe una posibilidad de obtener un prisma de acreción.
Porque también la pregunta continúa y dice qué variación podría existir comparado con una subducción tipo flat slab.
Flat slab, steep slab. Flat slab es más o menos, esa geometría es dictado creo, por la tasa de convergencia en la placa oceánica. Y también, aún más por la edad de la placa. Una placa joven es muy livianito, y una placa vieja muy pesado, y la placa pesada está entrando al manto más fácil, sí, con una ángulo de subducción más steep, más grande, sí. Pero esa diferencia entre slab, amagmatic flat slab y un ángulo produciendo magmatic arcs no ocurre solamente en la situación actual del margen andino, pero también durante toda la evolución de los Andes en diferentes edades, en diferentes zonas de los Andes. Es una cosa muy típica.
Acá quien hizo la pregunta la replantea y pregunta si la geometría de la subducción controla en algo el desarrollo de ese prisma de acreción. Si el prisma está relacionado o controlado por la geometría de la subducción.
No, no tanto. Bueno, la acreción ocurre solamente si hay material de acrecionar. El ángulo de la zona de subducción controla donde el marco, el arco magmático está desarrollando. El tipo de acreción, así que he mostrado, acreción frontal versus basal, está controlado más por el estado térmico, o sea, por el gradiente actual en todo el sistema. Ese quería mostrar con esa pantalla con la dehidratación. Acreción frontal ocurre primero siempre. También en esos modelos análogos está seguido por acreción basal. En ese al inicio tenemos un gradiente más alto, entonces material puede ingresar solamente a poca profundidad hasta que están en una zona donde dehidratación es posible. Agua sale. Agua hace la roca más floja y ayuda el proceso de acreción. Si todo el margen enfría, que es muy, muy típico en muchos márgenes, observado en muchos márgenes en todo el mundo, entonces el material, las gravacas pueden llegar hasta una zona más profunda, hasta que están en una zona donde dehidratación es posible. Entonces están acrecionados en una profundidad más profunda que durante el proceso de acreción frontal.
Bien. Bueno, Flor, no sé si hay más comentarios en el chat de Meet.
No, en el chat de Meet solamente tenemos saludos del doctor Carlos Cingolani, que está muy agradecido por la exposición y le deja un saludo al doctor Willner y agradece a todos los colegas que participaron de la discusión y a los organizadores. Y luego un saludo de la doctora Renata Tomesoli, que le agradece por la charla y le desea unas buenas tardes después de esta charla que nos ha brindado.
Es muy oscuro ahora aquí. Ya, es completamente oscuro ahora. Pero un lindo tarde de verano. Sí, vamos a continuar capaz con un vino en el jardín.
Muy bien.
Escasamente no puedo invitar a todos ustedes.
La doctora Melissa Angeletti también le deja un saludo al doctor Arné y le agradece también por la charla y a todos por la organización. La doctora Lina Tibaldi también le agradece a Arne por su charla tan interesante. Así que no sé, Flor, si hay...
disculpen los problemas técnicos al inicio.
No hay problema. Gracias a usted por tomarse el tiempo de armar esta charla tan interesante y por brindarnos su conocimiento a través de esta presentación, que agradecemos mucho.
Bueno, gracias a ustedes para escuchar.
Agradecemos a todos quienes participaron en esta charla. En nombre de la Comisión de Petrología Ígnea y Metamórfica de la Asociación Geológica Argentina, Arne, te agradecemos por tu tiempo y por compartir tu conocimiento con nosotros. Y les comentamos que la próxima charla de la comisión estará a cargo de la doctora, ¿cómo es el apellido? Me olvidé.
Estará a cargo de la doctora Larisa Dobrinchenka, que nos hablará acerca de los diamantes en zonas de ultra alta presión. Su charla se denomina Small Diamonds and Big Concepts y bueno, será el miércoles de octubre a las 15 horas por el Zoom de la Asociación Geológica Argentina, así que para quienes estén interesados de participar en esta charla, pueden comunicarse con nosotros.
Bueno, muchas gracias.
Bueno, le agradecemos a todos por participar.
Sí, chao, muchas gracias.
Bueno, ¿cerramos?
Amén.